Welcome to the Deep Dive, the show that cuts through the noise and gets you straight to the heart of what matters in the universe. Today, we're tackling a really big one, the Big Bang Theory. It's the main story science tells us for how our cosmos began and evolved, and frankly, its successes. They're pretty spectacular. For decades, it's really shaped our understanding of, well, almost everything out there.
It really has. It's a huge achievement, no doubt about it, a framework that's given us incredible insights and stood up to a lot of testing. But like with any frontier, right, there are these little intriguing observations, these theoretical bumps in the road that don't quite fit. They kind of nudge us to ask, is that the whole story?
Exactly. And those little bumps, those intriguing observations, that's what we're diving into today. Our mission is to go beyond the Big Bang, explore those discrepancies, and look at some alternative theories, ideas that paint a really different picture of the universe. Think of this as your shortcut, getting you up to speed on the cutting edge of the debate. Not just what scientists think, but why some are looking elsewhere. So, yeah, buckle up. We're heading into the cosmic curious zone where what we know meets, well, what we don't know yet. Okay, so before we jump into the alternatives, we need to understand the ground we're standing on, the current champion, if you will, and that's the Lambda-CDM model, the standard model of Big Bang cosmology.
That's the one. Lambda-CDM or SCDM. It's basically built on three main things. First, there's lambda. That's the cosmological constant linked to dark energy, pushing the universe to expand faster and faster. Second, cold dark matter, CDM. This invisible stuff supposedly provides the gravitational scaffolding for galaxies and big structures. And third, ordinary matter. Stars, planets, us, everything we can actually see. And it all assumes Einstein's general relativity is the right way to think about gravity on these huge scales.
And it's had some major wins, right? These aren't small things.
Oh, absolutely. Huge wins. CDM does a fantastic job modeling the cosmic microwave background, the sort of echo from the Big Bang. It explains how galaxies are spread out across the universe, predicts the amounts of light elements like hydrogen and helium really well, and it accounts for that accelerating expansion we see. It's been, the workhorse model for decades, explaining a ton of observations.
Okay, those are impressive, really solidifies its place. But even with all that success, were there always little hints of trouble? Or is this mostly new stuff from better telescopes? Because even the best stories can have plot twists, right? What happens when the observations just don't quite line up?
That's a great question. It's a mix, really.
Yeah.
Some issues are clearer now because our instruments are just so much better. Others have been kind of lurking. One of the biggest ones people talk about now, something really giving cosmologists pause, is the Hubble tension. It's this statistically significant problem where the Hubble constant of the universe's current expansion rate gives you different values depending on how you measure it.
Huh. So it's like using two super accurate rulers on the same thing but getting different measurements.
Exactly like that. If you calculate it using data from the early universe, like that CMB radiation, you get one number. But if you measure it using stars and supernovae in the late universe, closer to us in time, you get a different number. And it's not a tiny difference either. It's persistent, it's statistically solid, and it's a major headache for ACDM. It hints that maybe we're missing something fundamental.
And it's not just the expansion rate, is it? The model leans heavily on stuff we can't actually see. Dark energy, dark matter, that's indeterminate physics. That's got to be a problem, right? We're saying most of the universe is made of stuff we haven't found.
It's a huge challenge, a profound one. I mean, think about it. Decades of searching. Underground labs, giant particle colliders, telescopes looking for subtle effects, and still no well-agreed direct detection of a dark matter particle. Nothing conclusive. And dark energy, even worse, almost impossible to probe in a lab. And the value we observe for it is tiny compared to theoretical predictions, like orders and orders of magnitude off. Having 95% of your universe made of things you can't find or fully explain, that's a vulnerability.
Okay, wow. And then there's the bedrock assumption, the cosmological principle, that the universe looks the same everywhere and in all directions on large scales. It's a neat idea, makes the math easier, I guess. But is it actually true?
Well, there's growing evidence suggesting maybe not perfectly. For isotropy, looking the same in all directions, we see hints from galaxy clusters, quasars, even those type Ia supernovae. The Planck satellite map of the CMB, our best picture of the early universe, even shows this weird hemispheric bias, like one side is slightly different from the other. That shouldn't be there. Plus, our own motion compared to really distant objects seems different depending on what you measure against. It's odd. And homogeneity looking the same from everywhere. While some claims of giant structures breaking homogeneity haven't held up, there are findings suggesting maybe the universe isn't quite as uniform as we assume. at least on certain scales. Maybe our patch isn't typical.
And this is the one that gets me, and I think a lot of people find weird, the anachronistic galaxy problem. Galaxies showing up looking way too old, way too early. It's like finding, I don't know, a fully built skyscraper on day one of construction.
It's a critical point, yeah. In CDM predicts the most distant galaxies, the earliest ones we see, should be young, small, kind of blue, mostly first-gen stars.
Yeah.
Makes sense, right? They haven't had time to mature. But telescopes like Hubble, and especially the James Webb Space Telescope, JWST, are finding these big, old-looking spiral and elliptical galaxies way back then. They're packed with old red stars, lots heavier elements, high metallicity, which means stars must have lived and died already to create them, and incredibly high redshifts, meaning very early cosmic times, like CLJ 14490856, seen when the universe was supposedly super young.
So yeah, cosmic senior citizens when the universe was still a toddler, that just feels wrong, according to the standard story.
It certainly raises questions. And then there's the anachronistic supermassive black hole problem. We're seeing black holes that are way too massive for how early they appear. They seem to have grown incredibly fast, maybe too fast for standard models. Now, some early JWST candidates for massive galaxies turned out to be bright because of active galactic nuclei, which kind of skewed the mass estimates. But even the confirmed high redshift galaxies are often brighter and look more massive than simulations predict. They might not break the absolute limits, but they're pushing them, suggesting structure formation might be faster or different than we thought.
So the timeline feels off, but it's not just the big structures, right? There are issues even with the dark matter itself, assuming it exists.
That's right. Even within the dark matter framework, there are discrepancies on smaller galactic scales. There's the cuspy halo problem. Simulations predict dark matter halos around galaxies should be really dense and peaked in the center, but observations suggest they're flatter. The dwarf galaxy problem. Simulations predict way more small dark matter clumps, potential homes for dwarf galaxies, than we actually see orbiting galaxies like ours. And the satellite disk problem, dwarf galaxies around the Milky Way and Andromeda seem to be orbiting in these thin, organized planes, not randomly scattered like simulations suggest. Though some new work suggests that last one might just be a temporary arrangement.
It does sound like a lot of little things that aren't quite fitting together smoothly. When you list them all out like that, what's the vibe among cosmologists? Are people thinking, okay, new physics soon, or more like, we just need to tweak the model?
It's definitely a mix. I'd say most still have confidence in the core CDM framework, thinking it needs refinement, not replacement. But there's a growing number, for sure, who see these accumulating issues as signs of something fundamentally missing, or maybe even wrong. These aren't just tiny measurement errors anymore. They hit at core assumptions. Like, there's also the cosmological lithium problem. The amount of lithium we see in the universe is about 3 or 4 times less than ΛCDM predicts should have been made in the Big Bang. Lithium is fundamental, one of the first elements. That's a big mismatch for something so basic.
Right, not just tweaking numbers there. And didn't some Planck data even question the universe's shape?
Exactly. ATDM generally assumes a flat universe, which fits nicely with the theory of cosmic inflation early on. But some analysis of the 2019 Planck data surprisingly hinted at a slight positive curvature, a closed universe, more like a sphere's surface. That would potentially contradict flatness and inflation as we usually think of it.
And the last point I saw mentioned really hits at the scientific method itself, this idea of conventionalism.
Ah, yes. That's a serious critique. The argument is that CDM has become maybe too flexible. When observations don't fit, the response has often been to add new things like inventing dark matter or then dark energy, these sort of ad hoc stratagems, rather than questioning the core model. It raises questions about falsifiability. Is the model truly predictive, or are we just continuously patching it up so it can't be proven wrong? That's a major concern for any scientific theory.
So it's like we keep adding epilogues and footnotes to the story whenever there's a plot hole, instead of maybe rethinking the first chapter?
Yeah.
That's a strong point.
Precisely. At what point do the patches, the additions, become more complicated than the problem they were meant to solve?
Okay, this is where it gets really interesting for me. With all these cracks appearing, what are the alternative ideas bubbling up? What are the other ways people are trying to imagine our reality? Let's get into some of those what-ifs.
Well, one really fundamental alternative actually goes back to Edwin Hubble himself, ironically. It's the idea of energy redshift. Instead of saying redshift happens because galaxies are flying away from us due to expanding space, it proposes that light itself just loses a tiny bit of energy as it travels over millions, billions of years through intergalactic space.
Like a tired light effect, the light just gets worn out on its journey.
Exactly, that's the term often used. Hubble himself was apparently quite cautious about the expansion interpretation. He noted that if redshift isn't mainly about velocity, then suddenly, well, there's no proof of expansion, no limit on the universe's age, no need for spatial curvature. It opens the door to a potentially infinite, maybe eternal universe without a Big Bang beginning. Some even argue this tiny energy loss could be linked to things like radioactive decay phenomena, showing energy isn't perfectly conserved over cosmic timescales, aligning with nature's tendency towards entropy or disorder.
Okay, if light gets tired, what does that do to the cosmic microwave background? CTM sees it as the smoking gun for the Big Bang that left over heat.
Right. In an energy redshift view, the CMB might not be from one specific event. It's interesting. Way back in 1941, decades before the CMB was accidentally discovered, a guy named Andrew McKellar actually calculated the temperature of interstellar space to be about 2.7 Kelvin, just based on molecular observations. Later studies, like one by Michael Ibison, suggested that starlight, traveling through an eternal universe, would eventually get thermalized, basically averaged out in temperature by interacting with intergalactic plasma. It would inevitably settle around that 2-3 Kelvin mark. So the CMB could just be the combined redshifted thermalized light from countless stars over countless eons in a steady state or quasi-steady state universe, not a single echo. This view even recalculates the redshift source of the CMB peak to be much, much further away, consistent with a vastly larger, older universe.
Wow. Reinterpreting the CMB like that, that's a huge shift. Okay, so that challenges expansion via tired light. What about theories that keep expansion but change what's expanding or contracting? I read about the pan theory, where matter shrinks.
Ah, the pan theory. Yeah, that one's really thinking outside the box. It's a kind of quasi-steady state idea, much older universe than the Big Bang suggests. The core idea is super counterintuitive. Space isn't expanding. Instead, matter itself, atoms, everything is very, very slowly getting smaller over time. Like 1 part in 1,000 every 8 million years, roughly.
Yeah.
From our perspective, as shrinking observers looking out, this makes everything else look like it's receding, makes space appear to expand. And that alone could explain redshift.
That is completely mind-bending, but the claim is this single wild idea actually solves a bunch of CDM's problems.
That's the claim, yes. Because it proposes a constant density universe that's incredibly old, and where things are shrinking, it sidesteps the horizon and flatness problems. There's been plenty of time for things to homogenize, and flatness is just the natural state. It tackles the density problem by saying galaxies look less dense further away simply because our standard distance calculations, based on expansion, are long. The actual density, pan theory argues, is constant, and those anachronistic problems, old galaxies, massive black holes, high metallicity early on, no problem if the universe is vastly older. They've had ages to form everywhere. There's no cosmic dawn rush.
And it has this different idea about gravity, too, right? Using an ether and getting rid of dark matter.
Yes, another radical part. Pan theory brings back a kind of ether, a universal medium made of hypothetical pan particles. And it proposes gravity isn't a pull, but a push. Differences in pressure and flow in this ether medium create forces that we perceive as gravity, magnetism, even explaining waves like light as actual physical waves in the ether pilot waves. This mechanical pan-gravity using vortex mechanics could explain things like galaxy rotation curves and gravitational lensing without needing invisible dark matter. And interestingly, there is some lab work with vibrating oil droplets that behave uncannily like quantum particles with pilot waves, lending some perhaps analogous support.
So a totally different mechanic for the universe, with maybe some faint lab echoes, and it changes how we calculate distances.
Completely. Pan theory derives its own formulas for distance and brightness based on matter shrinking, not space expanding. And proponents claim these formulas match the observed data from Type Ia supernovae, those standard candles, very well, producing a straight-line relationship without needing to invoke dark energy to explain the dimming of distant ones.
Okay, wow. Pan theory is a trip. What about plasma cosmology, focusing on electricity and magnetism in space?
Right, plasma cosmology shifts the focus from gravity being the only major player on cosmic scales. It emphasizes that something like 99.9% of the ordinary matter we see is actually plasma-ionized gas. Stars, nebulas, the stuff between galaxies. It's mostly plasma. So the idea is that electromagnetic forces must play a much bigger role in shaping structures than lecDM allows. There's the Alpha and Klein cosmology, for instance, proposing an eternal universe with matter and antimatter regions, where expansion is driven by annihilation at the boundaries. We even create conditions like the early universe quark-gluon plasma in labs now, showing how fundamental plasma physics is.
So using lab physics to think about cosmic structure.
Exactly. Anthony Perad did famous work simulating colliding plasma clouds, showing they could naturally form spiral shapes, like galaxies, through electromagnetic Z-pinches, basically,
Yeah.
currents pinching plasma together. He argued this could explain galaxy formation and rotation without needing dark matter. Now, plasma cosmology has its own challenges. Critics point out it struggles to explain the precise smoothness, the isotropy of the CMB as well as ECDM does, and also has difficulty matching the observed abundances of light elements like helium and lithium.
And the sources mentioned a few other quick what-ifs, just throwing out more possibilities.
Yeah, just briefly. Ideas like Stephen Wolfram's computational universe, starting with maybe millions of dimensions that collapse down to our familiar three, or the idea of a cyclic universe, a bouncing cosmology where the universe expands and contracts potentially forever, avoiding a singular beginning and maybe explaining some large-scale anomalies. Lots of creativity out there.
So we've got the standard model with its successes and problems, and then this whole array of really different alternative ideas. What does this all mean? How do we possibly test these things and figure out which picture, if any, is right?
Well, that's the exciting part, isn't it? This is where the action is. New instruments, especially things like the James Webb Space Telescope, JWST, and ground-based arrays like LMA and Atacama, are giving us unprecedented views of the distant universe. They're gathering the kind of data we need to start distinguishing between these models. We're looking for those specific smoking gun predictions that one theory makes and another forbids.
Like what? What specific observations could really help decide between, say, CDM and something like pan theory?
Okay, so a few key things. Galactic density. If we look really far back, do we see galaxies packed much closer together, as CDM expects for a younger, smaller universe? Or is the density roughly the same throughout cosmic time, as pan theory predicts? That's a big one. Then there's the very early universe, the Dark Ages. Does CDM hold true, with a definite point before which no galaxies existed? Or is it more like pan theory suggests a gradual fading into a sort of foggy horizon of ever more distant, older structures obscured by dust? JWST is peering right into that era, so we should get answers soon.
And the nature of those first galaxies themselves would be a clue, too.
Absolutely. Are the very earliest galaxies we find consistently small, blue, metal-poor, just starting out like CDM needs? Or do we keep finding surprisingly mature, complex, maybe even dusty galaxies with varied stellar populations way back then, which would fit much better with an older pan theory-like universe? These observations, coming in now and over the next few years, are really going to put these ideas to the test. They could either cement our current understanding or potentially force us towards a completely new paradigm. The data will tell the story.
Wow, okay. From the pillars of the Big Bang, all its successes, through all the cracks and questions, and into these really imaginative, sometimes bizarre-sounding alternatives like shrinking matter and tired light. We've covered a lot of ground. It's pretty clear that while the Big Bang model gave us this incredible starting point, the scientific journey, the story of the universe, is definitely not finished.
Not at all. The debates, the new data pouring in, it just highlights how dynamic cosmology is. It's a field that's constantly pushing, constantly questioning, and that's, where the really exciting breakthroughs happen.
So, here's something to think about, a little provocative thought for you. What if the universe we've been trying so hard to map? What if it's just a fundamentally different kind of place than we've imagined? And what amazing new principle of nature, as Hubble put it, might we stumble upon next as we keep looking deeper and challenging our assumptions? The universe keeps dealing new cards, and we're all just learning how to play the game, keep asking questions, and keep exploring.